So great to see quite a number of you join. I hope you had also a really nice session in the morning where you had listened to great talks that were conducted by Nick Clinton and also some of our parallel speakers. Most of our talks are recorded, so in case you had not attended any of them, feel free to check out the links. We will make most of these links available to you on YouTube, and also the materials if the speakers had agreed to share them with you. I think one or two talks probably were not recorded, so just to let you know, apologies for that. If some of the content was sensitive, we were not able to allow for that. So maybe I could just start with introducing Minerva. So thanks everyone for staying on till this late. We have an introduction to Google EarthEngine workshop that's conducted by Dr. Minerva Singh. She's a research fellow at Imperial College London, and she joined the Center for Environmental Policy at Imperial College London in 2018. Before that, Minerva was a PhD student and candidate from the University of Cambridge, and she focused on implementing data science techniques for quantifying the impact of forest loss on tropical ecosystems. She holds a master's in philosophy in School of Geography and Environment, and also a master's in Department of Engineering from Oxford University, and has 10 years of experience in conducting academic research at the interface of tropical ecology, data science, and Earth observation, as well as artificial intelligence. So Minerva had published 14 first author peer-reviewed papers in international journals, and she has also obtained research funding of approximately £275,000, that's a lot, since 2018, and also provided research consultancy and data science support to startups, industry partners, and the like. So we also, just to also mention a few accolades. So Minerva is a fellow of the Royal Geographic Society and Royal Statistical Society, and is an associate fellow at the Data Science Institute, Imperial College London. She has been a course instructor also for MOOC platforms at Udemy. So if you would like to catch up with some of her classes, you can also do so on Udemy, which is an online class platform. So Minerva, thanks so much for joining us all the way from the UK. I would also like to inform I would also like to inform the audience about the Q&A. Again, we're using Slido, but this is a different session. We are using it for EarthEngine SG2. So maybe Cheryl, if you could put it on the chat group, the website, and also the code. And we will be fielding the questions, in between the workshop. So feel free to post any questions that you may have. So Minerva, I'm going to stop share now, and I'm going to let you share screen.
Sure. One second, it's not letting me. Okay. One second, it's.
Sure, I think sometimes it takes a bit of time.
Yeah, one second. Good now. I don't know, it's not letting me share. Okay, now I can share.
Mm-hmm.
Yes. Sorry, had a bit of a scare. So, can everyone see me?
I can see the screen well. It is a full screen on my end. I can see your code editor.
Okay, excellent. So now, obviously, all of you, I've posted some videos here about creating training data for supervised classification data sets within Google EarthEngine, introduction to remote sensing. I have a whole lot of other stuff as well. So I'll just share the link to my YouTube channel here. So if you want to refer to those specific videos, the links had been sent in before, but this is where you can go. So now, basically what attracts me to Google EarthEngine, I always love to talk about that you have a huge plethora of data sets within Google EarthEngine, and the number is always increasing. I think now we have some data related to forest structure, etc., coming in. That's quite recent, but you get the access to the whole Landsat archive, the Sentinel archive, the MODIS archive, other land cover data sets, and so on, croplands and geophysical data. So, Google Earth Engine, it has a huge database of most of the data sets that you could hope for. And yes, you have the option of uploading your own data. And now, without much ado, I'm going to end. This is just one example of the kind of data sets you can access from Google Earth Engine and the scale of the data sets. But now I'm just going to start. So I want to focus on the first order of businesses. I'm going to teach you how to actually start reading in some of these data and start working with them. So I'm interested in WDPA, World Database on Protected Areas, the polygons, and I want to read these in. So any data set that you want to read in from this catalog, it could be literally anything. First thing is just, you just navigate to that data set. Suppose, I don't know, what do I navigate to? And it tells you that this is Earth Engine snippet will tell you how exactly you can read it into your code editor. So this is your code editor, and you can access it by going to code earthengine.google.com. Most of you must have done it already, and I hope you are here. So today I'm interested in this particular data set, EE feature collection, because these are vector data. So vector data are always presented as feature collections, and these are the different attributes which are present in this particular shape file. And obviously that will help us work through the data set. So because we work with JavaScript, we always declare our variables using the keyword var fc. And if I want to see all the protected areas of the world, then I just type this in, EE feature collection, polygons, and map dot. And by saying map dot add layer, we should be able to visualize whatever we have seen here, whatever we want to add. So you can always save your scripts like so and run. And because it's big, sometimes running this may take time. So these are the different protected areas of the world. So you can see these are the protected areas in the east coast of India. These are the protected areas in Southeast Asia, the Palawan Islands. All of it seems to be protected, and I'm not exactly surprised because it's a very important area for conservation. So basically, this is how you can read in any feature data. But obviously, now it may happen that you may not want all the protected areas of the world. And then you can focus on these specific attributes and start filtering your data sets. And being able to filter your vector data sets is very important. So I'm going to, I've commented out the code, and so that you do continue to have access to this. But so now I'm going to create another variable and say FC. So FC is the variable which stores all the protected areas of the world. So I'm going to filter that by saying fc.filter. And then EE filter. Dot equal to so equal. EQ always means equal. Now, I want all the protected areas of Thailand. So ISO 3 is the country code for all the countries, and that's a 3-digit country code. You can actually look up the different countries by going in and typing in ISO 3, and it'll give you the 3-letter abbreviation for all the countries in the world. Yeah. And then EE filter equal to marine, 0, which means that I'm not interested in the marine areas. And yes, you can even have greater than, say, GT or less than, but that depends on the situation. And if you don't want to run a chunk of code, you can always say, you can just comment it out by using these forward slashes. Okay, now let's pray that I don't get an error. Okay, I didn't. And I can do the same. And now ISO 3, for example, if I want it for Cambodia, then I think, if I remember correctly, it's going to be KHM. That is what it means for. Oh, sorry, my bad. I should have put it here. Let's see if I can get something. So, and these are the protected areas for Cambodia. So if you ever get stuck in life, just remember you have to look up the and yeah, with controls that you can actually, if you haven't saved your script, then you can go back to where you were previously. I'm going to save this now. And now if I want to just get the name of one particular protected area. So remember, again, I'm using these attributes because it had ISO 3, and that's why I could say ISO 3 Thailand equivalent to, and you can see the 3-character country code. But now if I'm interested in the name, then I have to obviously know the name, which is the name of the PA as provided by the data provider. And my data provider is UNEP WCMC. So you have to know the names of your protected areas, whichever one you're interested in. But now I'm going to filter according to this attribute name, the capital name. So actually, I'll just uncomment this. And now you know where I created a variable hkh fc.filter. So you are going to filter fc, which is your feature shape file, EE filter with a capital EQ. That's how these EarthEngine functions are coded. Name, Y, Ka, Kaing, which is a protected area in Thailand. I think it's close to Bangkok. Anyone from Thailand? I'm going to save myself. And now I've filtered down to this particular protected area. And this is how you can explore the different data sets out there and filter them. And these filtering techniques, they work for feature data sets. Now I'm going to move on to the second lecture. And yes, you will have access to all of these lectures. I think they've been, I've already provided the code, but if not, yes, I'll be happy to sort of let you have the code. Now I'm interested in the digital elevation model. So I've created a variable data set, EE image, USGS, SRTM, L1003. So as you see, we have a lot of different SRTM data sets. And you have the option to read any of these in. I mean, you're not, when it comes down to digital elevation models, everyone, I mean, you are basically spoiled for choice. So, you can just, like I put in DEM here, and yes, you can go and get any digital elevation model you like. So that's the one I ended up choosing. And the first thing about these digital elevation data sets is, let's just explore this one. See if this one turns up. You will get them as country-specific data sets. Oh, well. So with most digital elevation data sets, you can extract the elevation and slope. And that's one thing I'm going to do right now, which is get the elevation out. Sometimes we have multiple bands in the same raster data set, and then we actually select a band. So dataset.select, and assuming that band number is there. So just to give you an example, suppose I'm just interested in this. So EE image, it means that this is a single image, but it is going to have bands. So the band it has associated with itself is elevation. And for most digital elevation data sets, the band which underpins this EE image, the single image, is usually called elevation. Is going to be different for other data sets. So, whenever you want to select, you'll actually go dataset.select elevation when you are selecting that band. And that is what's going to help you select, basically get access to this particular data set. So, you can't jump in directly. You have to know the name of the band. But if you're working with elevation, without fail, it's going to be map.addLayer elevation. So now we can actually see the elevation of the whole wide world. And all of the code that I've commented out, you can uncomment it at leisure and, actually work with it and see what kind of results you get. Now, the best thing about digital elevation models is that we can compute slope with it, and being able to compute slope is quite important. So I create a variable slope. For that computation has been coded into this function terrain with a capital T, dot slope. And we always compute slope from elevation. You can even compute the aspect and things like that, but I'll just go with slope because that's just about the most common thing. Yes, and then we can go and set the center. So and that means map.setCenter, where we specify a latitude, a longitude, and the zoom value. So basically it'll just bring your Google Earth engine, this particular window, to this particular latitude, longitude. And then I can say map.addLayer slope. And then I can specify the minimum and maximum values, minimum 0, maximum 60. And I want to call this layer slope. So it won't be called layer 1 or layer 2. Like usually when I added in elevation 1, poor thing got called layer 1. Now layer 1 can mean a lot of things. Now we'll be more intuitive and call it, give it a proper name. And so because I set this as my center, this got zoomed in to this particular lat long location. And what you see over here is slope 1. So slope 1 comes here. This is layer 1. I can switch it off. If I switch off slope, then I get layer 1. And yes, in the viewer, you get multiple slopes, multiple layers. And yes, you can adjust them like this also. And now I'm interested in getting the elevation for, well, the slope for my protected area. So again, we have this protected area, var FCEE feature collection polygons. You remember this particular clip. Now we are back to that. I'm interested in that particular protected area. FC filter, EE filter, EQ meaning name equal to Huai Kai Kaing. That's what EQ is doing here. And now I'm going to clip. Now we obtained the slope for the whole world, but now I'm going to clip it to the extent of this particular protected area. So I create var clipped slope dot clip map dot add layer clipped let's see. So now it has been clipped to this particular extent. And you can see this is the slope variation of this particular protected area in Thailand. And this is how you clip your data sets. You clip your image. And here the operative word is image with a capital I, and I'll come to that later on. Clip image to a certain outline. It could be the outline of a country. It could be the outline of a protected area. It could be the outline of your town. I'm going to save this. Now, image is important. As you see, we had like one image, EE image. Just keep this in mind. And we read it in using elevation, specified the band, but you won't be lucky every time. Now, when it comes down to working with actual remote sensing data like Landsat data or Sentinel and so on, we mostly get something known as image collection. So I'm going to just open this. So when we work with like proper Landsat, remote sensing data sets, we get EE image collection. Again, this is S1, GRD if you want to read it. And why we get this is because in the bands, we have multiple bands, HH, HV, VV, VH. So now we've got 4 bands here. Now let's just go back. Let's look at Sentinel. So we have got surface reflectance data, Copernicus S2SR, surface reflectance. And now when you look at the bands, we get B1 to B12 to all of these. And these are basically the SCL class table. So we get an image collection. Now you can see why an image collection is an image collection and an image is an image. But ultimately, to do anything worthwhile with this image collection, we'll have to boil it down to an image, like to a single entity. And I'll come to that. So now let's just work with our image collections. First, instead of a protected area, now I'm more interested in a country. Again, US DOS LS1 simple EE filter EQ country _ NA Japan. And this is a data set which is present within Google EarthEngine. So yes, you can go and look it up. And that can give you the names of other countries as well, but I'm interested in Japan. Now, we create a variable var S22A EE image collection Copernicus S2SR, because that's what I'm interested in. So this is my image collection, and that's what I'm interested in working with. And I'm going to filter this first by area and then by date. So if I'm interested in the date, I have to keep in mind that these data set, they vary from 2017, March 2017 to September 2021. So I can't specify something in 2015 and I can't specify anything in 2022. So I have to specify whatever I choose to specify has to be within this date range. Always good to check that. Now we create a variable, which I actually did. So let's just see. var filtered s22a dot filter bounds. And the idea is it's going to filter my Copernicus data, these data set to the bounds of Japan that you see over here for these data, for these dates, dot filter date. So filter bounds, it filters your image collection according to a boundary that you've decided. In this case, I decided on a country, filter date, and you always put in like, starting year, month, date. And then in order to get this to do anything worthwhile, you say dot median, which will actually, this median acts as a reducer because you can't really work directly with the filtered image collection. It has to be, then you are going to basically get the median of all the images from the 1st of May 2019 to the 14th of August 2019. So you don't get all of them as discrete entities. You take the median of all of these images. And by taking the median, what you'll get is the median of band of B1 from May 2019 to August 2019, median of band B2. And yes, you are not stuck. You don't have to be stuck with median. You can take mean, you can take the maximum value, you can take the minimum value as you like. It's just that median is quite common. Print filtered. This will just print out your data set for you. Map.addLayer filtered. So now when you say dot median, your image collection in a way ends up becoming an image. And that's why it gets displayed like so, 23 elements, 23 bands, because you took the median of all of these bands. And yes, you can even have color composites. So map.addLayer, this is an RGB composite filtered. You just try to show B4, B3, B2. These are the minimum and maximum values. And now it's trying to load up. Let's see. This means that it's just trying to load it up. And this can take time. Oh, well, never mind. I'm going to continue. We can clip our data set because when you have filtered bounds, it ends up showing you imagery which goes beyond the boundaries, or which may go beyond the boundaries of Japan. So if you want everything clipped to a certain extent, then you say filtered. Again, this dot clip Japan, and you can do the same thing here, map.addLayer, clipped bands. You can specify any band combination you like. Let's call it RGB2 and run it. So you can see now it's trying to read in 4 images. This could take time because these are image collections. And we are trying to get it at a country-wide scale. Anyway, and this should basically read in these bands. But now what happens is what we want to do after this, and what we want to do after this is actually start working with the bands. I mean, displaying, they'll be displayed in their own sweet time. But one of the first things that we end up doing with these remote sensing data sets is that we like to compute vegetation indices from them. So I'm going to do that. I'm going to compute vegetation indices. And first I'm going to run through the previous code again before we start computing vegetation indices, which is var fc, EE feature collection, current polygons, var hkh fc dot filter, EE filter equal name hue khai kang, var s22a, EE image collection, var filtered, s22a filter bounds, hkh filter date, median. And yes, you can have filter bounds and clipping in the same operation like me. So dot clip hkh, that will ensure that I only get the bands which fall within the boundary of hkh, the protected area. And then yes, I can add it like this. So again, with median, my image collection ends up becoming an image. Not the best rendering, but yeah, sorry. I should have chosen a better band collection, but as you can see, my images have been read in. And it's not just 3 images that have been read in. The entire plethora of 23 bands has been read in for this particular study area. But now I'm only interested in calculating some bands, some vegetation indices out of this. And some of the common vegetation indices include NDVI and DWI, NBR. I'm going to compute them now. var NDVI. Now you have to know which band combinations go into making an NDVI or an NBR for the sensor you're working with. So I'm working with Copernicus S2SR, and first thing I'm going to do is filtered. Filtered dot normalized difference. Normalized difference. Basically, it's going to give me the componendo dividendo formula, normalized difference, then specify the bands. So for NDVI, it's NIR and red, so it's going to be B8. B8, B4.
Minerva, do you mind if I just interrupt you?
No, go ahead.
So we have some questions. I think they were requesting for your scripts to be shared.
Of course, I thought I'd shared them, but let me share them again. I'm happy to do that. Now, where on God's green earth is my? I think this should. One second. Anyone can read.
Yeah.
Let's see. Yeah. The scripts are for them because all the commented out code, they can work on it and play around with that in their spare time. Okay, so this is where they can access these data sets.
Great, thanks. I think previously we shared a different set of like like something like preliminary readings for the workshop, but
yeah,
I think this would work. Yeah.
And clone the Git. I mean, I don't know if they want to clone. I've never done this, but if they want to do Git clone, then they can do this also. I mean, I'm happy with both, and anyone can read, so they shouldn't have an issue. But it'll be good if they try to access the scripts while we are in the session.
Yeah. So I clicked on the EarthEngine script. I don't know if it is just me, but I don't seem to see the code on my end.
Okay, well, then let me do one thing. Let me try to send it. Basically, then I'll have to send it script by script because I thought I could send you the whole thing. But okay, so let me just get the link for this one and see if they can get. So this is basically lecture 4 that we are on. See if they can get it for lecture 4, because if they can, I'll just send it for every lecture.
All right, let me test that.
Of course, of course.
Now I see the code on lecture 4.
So I think I'll do it for all the lectures individually. And
yeah,
we do the same for var NDWI, filtered normalized difference, B3, B8. Again, this is a question of just Googling which ones you need, and var NBR, filtered, normalized difference. And basically the formula you get with this would be something like, so by normalized difference, it means B8 minus B4 divided by B8 plus B4. So normalized difference, basically it computes that componendo dividendo for you. You don't have to code this thing on your own. And this is how I've made a palette, a list of hex strings, var, viz, and this is a list. And things like FFFF is not a swear word, CE7E, all of these are different color combinations. Again, you can look them up. And then yes, you get to add multiple vegetation indices. So map.add layer, again, add all of these variables and DBI. So with NDVI, the maximum and minimum values are 0 to 1. So you say minimum 0, maximum 1. Palette viz, it will go and collect these colors. And this is the name we just go and give to our different bands. For NDWI, we get -1 to 1. So you have to know what is the maximum and minimum value you're gunning for. NBR 0 to 1. And again, we have done something similar for slope. So we get to, when we want to add layer, we can also define these parameters. Now let's run it. And again, this is taking time. I think it's, so something's turned up. So this is a vegetation index. Let's see which one turned up first. Yeah, the NDVI index. So you can basically see the, okay, no, it's the NBR, the normalized burn ratio. So yes, again, you can see the distribution of the values and how this is distributed across the study area. And this must be the NDVI. So a lot of brownness. And yes, you can change the color patterns and experiment with that. Now I'm going to move on to the next thing, which is unsupervised learning, clustering. And before I do that, I'm going to get the link. And
Thanks, Minerva.
Yes, lecture 5. This is for unsupervised learning. Just obviously, it'll be great if people check whether they can get it or not, but I'm sure they should be able to get it now.
Yeah, it works on my end.
Fine. Now, again, we have the same EE feature collection, protected areas, and I'll continue to work with the same protected area, var HKH, FC filter, EE filter, EQ name. Now, I'm just going to load up a pre-computed Landsat composite. And this Landsat composite is basically in the year format. So var input, EE image, Landsat, LE7, top of the atmosphere, 1 year, 2001. And yes, Landsat data, they do have these composite, and I'll clip it to the extent of my protected area. You just have to look it up. I mean, I'm just doing it for simplicity's sake. Otherwise, you do have the option of taking an actual image collection, working with it, and then basically drilling it down to an image. You can start with an image collection and bring it down to the level of an image. But here, just in order to save time, I'm going to, take an existing image. And yes, if I had an image collection, I would have applied median and reduced it to an image like I did with NDVI. So it's either you get an image, EE image, something like this, or you get an image collection and you apply a reducer. So a median is a reducer. You apply something like that to come to this level. And now we are going to make a training data set, and we are going to do the same for supervised classification, which I know everyone's waiting for. But I create a variable var training input.sample. So we are going to collect our training data from the input image, and the input image is the Landsat image, input.sample, and collect the sample points to feed to an algorithm. Region HKH. So this is the geometry that we focus on. The scale 30 because it's Landsat. The number of pixels 5,000. I only need 5,000 data points. Now, once I'm done there, I'm going to say, and there are other unsupervised algorithms worth checking out. But anyway, per variable clusterer, EE, clusterer dot Vecca means, oh, okay, come in. Vecca K means I think I've got 15 different land cover types. So I say I'm looking for 15 clusters dot train, and I'm going to put in the training data. That's it, training. So dot train implements the algorithm. So here I've defined the algorithm EE cluster dot Vecca means 15 dot train training, and it's going to use these training data sets. So, and the image to be clustered is the input. So I collected the training data sets from this image, and I'm going to cluster this image input. So var result input dot cluster clusterer and map dot add layer. So result dot random visualizer. So if you don't want to specify the different colors, you can actually see a result dot random visualizer, empty square, empty curly brackets, clusters. And let's see if we get anything. Yeah, basically these are the different clusters that we get. And as you can see, you know, it can actually identify patterns. So this entire chunk is one land cover type, and the same goes for this. This seems to be one land cover type. So yes, clustering is a good way of getting sense of the different land cover types or entities you may have in your image. And now let's move on to supervised learning. Now, the first thing about supervised learning is that it needs you to create your training data sets, and we typically do it by either defining the points or by drawing a shape or drawing a rectangle. So if I was to draw a rectangle, you know, yeah.
My apologies. I wanted to check in with you. With the previous code, you mentioned variable defining training and then input dot sample.
Yeah.
And this, I mean, on our end with the code, it states that line 15 input is not defined. Is that something that the audience have to do on their own?
Sorry, could you just type that out?
Oh, under the variable that's defined as training, equal input dot sample.
Yeah.
So I think that's line 15.
Yeah, that's it.
Is that something that like we have to create, or?
No, I mean, whenever you do it for your own data set, you'll have to create it.
So to create a set of sample points in order to feed into the classifier, right?
Yes, this is the training data set. So it'll create sample points to feed into algorithms.
All right. So is this that, was it mentioned earlier, or is this something that we are talking about in the next lecture?
Well, in the next lecture, we have supervised learning, and over there, you actually collect your data sets like.
Okay.
So basically, for that, I have these different data sets, and you have to collect the training data sets from here. Like I already had a link for this copy link address. So this is how you make training data sets.
Very cool.
Yeah,
Thanks.
so it's different for supervised and unsupervised learning. Yeah, but you'll obviously define the stuff. But this is something you have to do completely separate. So even before you start.
Thank you.
So
I think we have.
Yeah, so when I had these geometry inputs, that's what I did. I selected these different points. I called it, I gave it a specific name, and then, I went and collected all of these points and went on labeling them. So if I wanted to add a new layer, so it calls it bar geometry. If I add a new layer, I'll have to call it, okay.
We have 2 questions in Slido. Cheryl, would you mind?
And it'll have to be a feature collection. And then I can go, okay, I can give, ask me the question. I can go, okay. And then obviously go on selecting points all over the place.
Yeah. Cheryl, do you mind if you could read out those questions?
Yeah, I've got 26 points here. I've got 31 points, and then I'll, go on collecting my points.
Yeah.
Oh, okay.
Sure.
Sorry, I just found it. Sorry, I couldn't find it earlier. Go ahead, Cheryl. Yeah.
So Minerva, the first question is, does G also have climate data, such as from World Clim or CRU climate models? Can it read or process NetCDF files?
Oh, which files?
NetCDF.
CBF? Yeah, NetCBF. I don't know. It does have climate data sets, and but I don't think you have to process those climate data sets in NetCBF. Like, you'll have to read it in like this. So if you want climate data sets, yeah, we have those, but you can't process them like NetCDF files.
Okay, I think the second question is, how do you determine the number of pixels for training the unsupervised clusterer?
Oh, well, that depends on you. I mean, 5,000 is a good number. Remember, you can't have millions of points. So if you have a small area, like a protected area, 5,000 points or 10,000, I think that's sufficient. Of course, the bigger your area, the bigger your points. But aim to get at least 2,000 points, even for a small area.
Okay, I think that's all for now.
Great, thank you.
Okay. Thanks, Cheryl. Thanks, Minerva.
Great. Now, the first thing is that when I, for this lecture, I had a particular data set, and it wasn't an inbuilt data set of Google EarthEngine. So that was a feature file that I read in. So as you can see for this particular lecture, these are the training data sets I collected, and for the supervised classification. And I want to carry out supervised classification for this particular study area, Amazonian Bolivia. And I had a separate shapefile of its own, which I downloaded it from a national data set. And I've read that in. So if you have your own data set to read in, let me just, so this is one thing that you should know about.
If you don't mind sharing again, lecture 6 slide as well, or the link to the code.
No problem.
Thank you.
Get link. Lecture 6, here you are. So you have this new, so these are my assets that I had read in. I've read them in for a number of different countries, and this is for Amazonian Bolivia. So, and this is what my shapefile actually looks like. Now, if I want to work with these data sets and I want to import it, so I can, yes, actually import it like so. One. So this was a shapefile I read in, and obviously if you want to add new assets, so these are my legacy assets, you just go to new assets and you can go table upload. And then if you have that sitting somewhere in your system, then you can just select the source files and it'll tell you to select shape, zip, dbf, and so on. So I have all of these. For example, I have shape files like these. I don't have any shape files here, but if I did, then I'd just go to that folder and upload all the shape files that I need. So basically shapefile assets, you should be uploading the shape, the dbf, the proj, and then once you do upload, it'll be ingested into the system. Can cancel it. And that's how you get to add your own assets. And yes, you have the option of adding in things like images as well. So this is like another one. So map table 2. And these are the things that I went and uploaded. So, these are the different biomes of Brazil. And if I want, I had something for, and you can see the symbol here. I'm not going to read this in, but this was imagery data. So again, if you want to upload imagery data, you just upload GeoTIFF or a TFR record. So that's what my table means. That was the Bolivian Amazon. Now I have the VAR Landsat collection, EE image collection, the Landsat data. I filter it to the boundaries of Amazonia and Bolivia by defined in table dot filter date. So this is like a 1-year composite. Now, in order to make a cloud-free composite, I create a variable composite, EE algorithms, Landsat, simple composite, collection, Landsat collection. So I just put it in as float true, print composite, and then I get then I decide to create my image, var image composite clip table. So this is basically going to, what this does is it selects a subset of scenes, converts it to top of the atmosphere reflectance, and applies a simple cloud score and takes the median of the least cloudy pixel. So basically what I get in my composite is an image. I create a variable image, composite, clip table, and then I decide that these are the bands. These are the bands to input. So I won't have just one band, B1, B2, B3. I'm going to input that. Then I'm going to merge all my land cover geolocation data. So I've created all of these points. I'm going to merge them together into a variable called samples by saying forest. So yeah, I've created forests. Dot merge water, dot merge sparse, dot merge degraded. So all of these points, I'm going to merge them. I'm going to collect the training data, var points, image, select bands. So these are the bands we are going to collect our data from, sampling data dot sample region. So now we are going to sample the regions, collection samples. So these are the samples we will collect. And the properties are LULC because that's the property I had defined for them. I just open this. So this is a property I defined for it. And once you start defining your variables, you have to put in a property and you have to give it a value. And the first attribute gets the value 0. That's how it works. So that's why I specify properties LULC, scale 30.random column. Then I define a training data set, basically by splitting my data sets into 75-25, var training, points.filter, EE filter, LT, random, 75. So LT is less than. So we just select 75% into training, points filter, random, 75. And the remaining 25 will go into testing. And then I call a classifier. I create a variable classifier, EE classifier libsvm.train. And this is defined within Google EarthEngine. So classifier.libsvm.train features training. So I'm going to put in these 25% data set for training. The class property is LULC, because that's what I want to classify. And this is, and I'm going to input the bands here. Then we just classify, var classified image select bands. So we select these bands to classify on dot classify classifier, map add layer clip table. So I've got 4 classes. So I say 0 to 3, and I give them these 4 different colors.
Minerva, sorry to interrupt. We have 2 questions on Slido.
Yeah.
I mean, the first question is about getting the link to all example codes. I mean, we've already shared lecture 4 to 6. I think later we can.
I'll share all the others also once I finish this.
Yeah, then we could share 1 to 3. Another question, in a multi-band raster, how do you determine the maximum and minimum of a certain set of bands? Example, maximum B1, B4, B10, and
You have to
minimum.
look up the literature. You have to look up the literature.
Mhm. So this depends on the image that you're looking at, right?
Exactly. That depends on the data set you're looking at.
So for example, if it's a Landsat band, which is a multi-band, I guess, you know, these values would vary for each of these separate bands within the Landsat image, right?
Yeah, I think you'll have to look it up from the lookup tables.
Yeah, and I think this is also available on the data catalog. They also mentioned.
Yeah, I think it's mentioned in the data catalog. So they'll have to simply read it, which ones are available.
Right.
Okay, I'm sending over the links to lecture 2 and 3 while at it. I mean,
sure.
I hope I've.
Yeah, I hope that answered the question earlier. If you have further questions, feel free to input into the Slido link. And we will compile the links from Minerva's multiple lectures.
Yeah, and this is lecture 1. Where was I?
Right.
So this went and collected that. And this is a question of, again, now we want to validate it. So again, I take the validation data set, validation.classify classifier, print validated validation, bar accuracy, LULC classification. So we get the error metrics, which is this, and we compute the overall accuracy, which is by computing accuracy, which tells me that my overall accuracy is only 65%, which is not very high. Basically, this is a very simple way. And this is a very crude way of carrying out supervised learning, but whatever you choose to do, this is the workflow you'll end up following.
Sorry to interrupt again, Minerva. I think one of the questions redirected to the chat group. If you could look into the chat. It's from Muhammad Ashad, and he asks, so you took training samples for classification by changing the band combinations and seeing the appearance of pixels in different colors in different bands?
Yes, that's one way of taking your training sample data sets, or you already have a CSV file which has these data sets, or a shape file which has these data sets. Personally, I prefer that you get a shape file which has all of these data sets available to you, and you read that in. Otherwise, you'll just have to, look at those different false color composites and think, okay, this looks like a forest to me. This definitely is a lake. That's one way of doing it. But if I had to print a paper or publish a paper, that's not how I'd do it. Then I may just go, I did it several years ago. Let's see. Where on God's green earth is that? Let me see how I'd do that. So yeah, this was a data set that I had. So I actually had unburnt, and I had latitude and longitude for it. And I read in the whole shape file. That's how I'd work with it. But of course, if you don't have that, and yeah, I had the file type integer assigned to it. But if I don't have the luxury of doing that, then yeah, look at those false color composites and, just randomly call this thing And I've actually imported the geometry and just randomly call it a forest.
We have 2 questions in Slido.
Sure.
Sorry to interrupt your session.
Oh, that's okay.
So one question, have you sampled with NICFI images for land use and land cover classification in EarthEngine?
Nope, I've never used them. I mean, I think they're mostly available for the United States of America, and I don't work so much in, I don't work with American data sets. So no, I've not used those. This is your lecture 8. In case
And
I
then,
can't lecture 8, then you'll have it here.
Thanks for sending those. And then the second question, is it possible to do post-classification steps in GEE? Example, pixel-based change, transition matrices, etc.
I think it should be possible, but that's not something. And they have new algorithms for, let's just see, for change detection, but I've never used them here. I mean, for me, I'd get my maps out and I'd actually do them in QGIS, but let's see. I mean, you do have change land cover detection kind of data sets. And yes, I suppose they could be used. I think it's a question of looking it up.
Yeah, I do think that you can calculate the error matrix
Oh,
if you
yeah.
do a land cover change analysis. And I think in Nick Clinton's talk, he did talk about temporal changes, like doing some analysis with NDVI.
Oh, yes, I think
So-
you could temporal change analyses.
Yeah, great questions. Thanks so much. So continuing with lecture 7 and 8.
Yeah. Now, this is a particular data set that I'm interested in, and that pertains to night lights. So VAR, and these are the data, EE image, and these are the night lights data. We select the stable lights and we clip it to collection Japan. And we define night lights. So this was a very crude attempt at carrying out zonation, VAR zones, NL2 greater than 30, add NL2 greater than 55, add greater than 62. So we are interested in creating these 3 zones of night lights, and we create a variable zones, update mask zones, not equivalent to, and we convert zones to the thresholded night lights, and we try to convert these to vectors. So basically, this is a raster to vector conversion. Zones dot add bands NL2. So we add our night lights to these zones, and then we reduce to vectors. The geometry is Japan. The CRS, we get the projection of our night lights. The scale is 1000. With the geometry type we want is polygon. We don't want anything complicated. Label properties zone. And the reducer is mean. So average night light values for these zones. Again, set center. Since we have 3 zones, we just give them 3 zones. Let's see if this runs or not, because this is a very old chunk of code, but it's a good example of reducing your rasters to vectors. So basically with this, you can actually create categories. So again, that's something you could do for NDVI. So if you had 3 NDVI categories, instead of NL2 greater than 30, NL2 greater than 55, and 62, you could have NDVI categories, and you could actually visualize them like so. And then I have a data set on rainfall. Again, this is how you create charts and this one is it's computationally intensive, so it may not run because it has data sets for, sometimes the system times out, so you have to try it a couple of times to get it to run. But here, anyway, we have a variable for countries, WTPA polygons. Now CHIRP's data set, EE image collection, is the data set for rainfall. And then this is the data set for land cover, EE image collection. So we can start and end and have an end date, var start date, end date. And we can have EE date from year, month, day, and from year, month, day. So this is my starting point, 1981, before I was born, and 2019 December. And then we create a sequence for years. So for years, we create a sequence from 1981 to 29. For months, we create a sequence to 1 to 12. I have the country of Thailand, var Thai countries filter in list, country NA Thailand. That's one way of filtering out your country. Again, I do the same. I filter out my protected area, and then I need to get the geometry of it. So Thai.geometry, that will obtain the geometry of these shape files. Var rain, so chirps, I'm going to select the band. Remember, this is an image collection and I need to select the band, which is precipitation. Filter dates, again, I take the start date and the end date, and filter bounds, which is HKH by its geometry. Print all and print chirp images. And var rain year list. So this is a simple function where I take the years, dot map the function, var rain all, this one, e filter calendar range, sum, name it the rain year, return rain year, set the year. So we set the year where that's 20, it will start from 1981 to 2019, and then go like this. And essentially, we'll try to run this. Okay. And basically it will try to produce the annual rainfall for Thailand from 1981 to 2018, and it will try to generate a chart of the rainfall if it doesn't time out, basically. And this is how we get the rainfall annual, dot select rain year, dot min, clip to Thailand, and we can get the rainfall for Thailand. And if I clip it to the geometry of my shapefile, then I can get the rainfall over my protected area from 1981 to 2018. And this is how we basically, this is one way of generating charts within Google Earth Engine. And this is going to take quite a bit of time. Does anyone have any questions? I mean, we can wait for this to finish, or you can run this code at your end and see what kind of rainfall charts you get. Hello, any questions?
One question in Slido. I think, let me just have a look at the slide. Hi, Minerva, do you have any tricks or tips to sense if a particular workflow may be too large or computationally intensive to run on EarthEngine? Apart from clearing out my hair, I don't have a lot of suggestions. One way of going about is to work in Google Colab, but then instead of JavaScript, you'll use Python. One of my students, he was working on a project, it needed Google Colab, and ultimately he managed to time out of that as well. And he had to go in for Google Earth Pro. I think the university had to pay for it. All right, thank you. You can export the results, resulting feature layers from Google Earth Engine. Yes, I mean, I haven't covered that part, but yes, you can sort of, I mean, it's a question of just going and Googling, but yes, you can go and export your data sets. And see, this is like generating, it will generate, and it will very easily time out on me. So yes, I think when I get the chart, I managed to get it, but it's a bit of a hit and trial. We have a question from Muhammad Ashad in the chat group. He said, can you please go back to line 30 for function mapping and re-elaborate if possible? So basically we have the years, we are going to map the function. So we take the rainfall, we take the precipitation from that particular point and filter the calendar range for the whole year and do it year by year, sum it, and then rename it rain year. And then we just return the rain year. Thanks, Minerva. Another question from, is that the end? Are you going to elaborate a bit more?
Yeah, I mean, sorry, this is all that is to it.
Okay. The question from Chong Kwek Yen. So he asked, can you export the resulting features
Yes,
on
yes,
layers?
I'm sure, yes, of course you can export it, and let me see. I must have, I mean, I'll have to look up my other scripts, but let me see if I had something to export. Did I actually export something? I mean, you just have to, let's see. Yes, you can export. So this is what I did, export image to drive. So this was the image I clipped. So, you know, I managed to calculate everything, the full works. This was the image, the variable that I want to export, clipped. I give it a description. I can give it a scale, and I can give it a region, polygon. And I must be having a polygon somewhere. So yeah, so it seems that I had a polygon somewhere, and that becomes the extent I want to carry out my export to. So if I ran that script, it would basically let me save it in my Google Drive, and I can specify a folder like so. So basically this is what you would do.
Thanks, Minerva. I think the export is also going towards the Google Drive that you have. So your own Google account. At least that's what also is for my end. And, you know, of course, if you have limited data in your Google Drive, then it could be a problem when you're exporting something very data intense.
Yes.
We have a question earlier, I think this one from Muhammad Ashad again. And in output, we got total accumulative rainfall from 1981 to 2018 over the region, AOI, area of interest. Yeah. I think that's referring to your previous...
Yeah, that's what we are trying to get. I think this is a very useful, I think we could send this around as an email, that band combinations, about, you know, band combinations. I think that may be useful for a lot of people.
One question in the Slido: what happens when the script times out in EarthEngine? Do we have to rerun the script all over again? Or can we resume it from where it stopped?
No, you'll have to rerun it and just hope that it works.
So a lot of luck in some ways. One from Budi Fajar Supriyanto. The blue spot in the map, that is rainfall area or water body, and then how we identify the different rainfall and water bodies. Thanks so much.
That's just a shapefile. I mean, defining water bodies and rainfall, I mean, that's going to be a completely different lecture.
Oh, sorry, I was mute. There's a comment from Isiang. To the user who asked about band combinations, you might find the following resource from Portland State University quite useful. For indices, including NDVI, usually these are documented well by NASA EOS pages, as well for band combinations or recipes. Thanks so much, Isiang, for sending that resource.
Yeah, I think that's very useful. Maybe we could send an email around to everyone, you know, pointing them to these resources.
Yeah, I think I will be, let me see, I could also just copy and paste. I just sent this, this Google sheet, which has got the varied resources that you had sent around, one from the preliminary set of like YouTube links to check out. And I'll just put here a comment from Yi Xiang so that we have it captured in the Google, the Google sheet that I sent around. So this has got a list of all the slides that you sent, the web links that you sent from lectures 1 to 18.
Absolutely.
Yeah, thanks so much, Minerva.
Welcome.
Is this the end of your lecture or you have more?
Oh, this is the end of it.
All right, great. Thanks so much. I think we want to show our appreciation for Minerva. So maybe just a round of virtual applause. Thanks so much, Minerva, for
thanks for having me. Wonderful interacting with all of you.
And thanks so much, everyone, for joining for the introduction. And Cheryl, you want to say something?
For joining today's event. That's a very interesting demonstration, and I think workshop. I think we have a lot of people in this room, so thank you very much for your interest, and we do hope to meet you again in the next events.
Of course, I'll catch you soon. Thanks so much.
Yeah, I agree. Definitely by using EarthEngine, like how you have done, giving us these codes and then like playing around is the best way to go to try to learn how to use EarthEngine. So these are very helpful. Thanks so much, Minerva.
Welcome, welcome.
All right, take care, everyone, and we will be ending our session. Thank you for joining.